right? So here's my atom I'm drawing. I have 1 proton, and that also indicates the number of electrons that you'll have, because for a neutral atom, you'll always have the same number of protons and electrons. So what have I drawn here? What is this thing? Hydrogen. All right? I draw another hydrogen, and I draw this 1, 2, 3, 4, 5, 6, 7, 8 positive, sorry, 6. 1, 2, 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. I'll throw in some neutrons too. Electrons. 1, 2, 3, 4, 5, 6. A couple more. 7, 8. All right? So I have 2 hydrogens. What was this thing that I just drew? Oxygen. So I'll put an oxygen there. I'll remind ourselves that these are hydrogens. The overlap that occurs between the electron density here and the electron density here becomes a bond. And this is our molecule, right? Our molecule, which is what? Water. Okay? That's our molecule. All right, so molecules. Now the word molecule has a synonym. Well, I don't know if people would necessarily agree with this, but it's synonymous with the word modular. Modular. Now that's not a word that we use a whole bunch, but in Idaho, when I was going to school there, they would sell modular homes. Does anybody know what that is? A modular home? What does that refer to? Like what?
Like the Hubble home?
Hubble? I don't know. Is that a brand name? What would they do with them?
Like build your own house.
Build your own house? Okay, so there was some pre-selected plans. You'd make little modifications and stuff and say, this is the one I want, and then what would they do?
Okay, then they build it.
And then what?
Charge much money.
Well, I'm not sure about Hubble homes, but the modular component of a modular home is they would drive it up on a truck and then put it where you wanted it, right? And sometimes, depending on the size of the home, it would take 2 or 3 trucks for them to bring in the modules that would make the whole thing. Okay? So a modular home is one that comes in like units. Something that's molecular, it kind of interacts with its surroundings in units, like that. So water is an example of a molecular compound, right? Water is an example of a molecular compound. I'll write that down. Sodium chloride, NaCl, is that new for anybody? Raise your hand if that's new for you. Okay, so sodium chloride is an example of a compound that's not molecular, but it's ionic. So that means that instead of being in little groups of sodium and chlorine, it's in what we call a 3-dimensional lattice. You have sodium ions and chloride ions alternating like this. Not just in a chain though, in 3 dimensions. So here's my 2nd dimension. Let me see if I can draw a 3rd dimension. I don't think I'm going to be able to. So it becomes like big one, small one, big one, small one. They're getting smaller as they go quick, right? We have some good pictures on the thing, but it's just fun to draw. So it's hard to stop too, because you're like, hey, we got one more after this, right? But so this is a 3-dimensional lattice, we call it, a 3-dimensional lattice. So this is how sodium chloride resides. And you know, you put it on your food, right? The little sprinkles that come out, if you look really close, you'll see that they're box-shaped, right? They're cubic, right? Whereas water is molecular. It's just this little unit that goes around and does its business like that. Now we can identify compounds that are molecular and or ionic relatively easy, and I'll show you the relatively easy way. There are some exceptions, and that's something about chemistry. There's always a little tiny bit of exceptions, and as you get more complex, the exceptions increase, and you know. So the way that is most effective to identify whether the compound is ionic or molecular is ionic compounds contain metals. Right? They contain a metal. Molecular compounds, no metals. All right, so now all we need to do is identify where the metals are on the periodic table. And the periodic table is actually nicely separated in such a way that one side is made, or is all the metals and one side is all the non-metals. And the staircase here is this green little section. And if you look at the front cover of your periodic table, if you have your book, open up your front cover and look at the periodic table there and see if you can find that front section. Is everybody here? All right, did everybody get the roll? Everybody got the roll? So, were the new people on the roll? Okay, awesome. Okay, if you didn't get the roll, make sure you come and sign it. But can you see the staircase on there? Front cover of the book? Just absolutely front cover, just right up against the front cover. Can you find the staircase? It's white. Oh, you got the first. Okay. What side do you think is the metals? Left or right of the staircase? Oh no, did you get that book from the bookstore?
I got it from my friends.
From your friend? Oh. This is the right book. Where's your periodic table? Oh, you ripped it out. What's going on? Well, see, I told you, there's always exceptions. Anyway, so, what side? Left or right? Which side's the metals? The left. We can tell because we see things like iron, magnesium, I don't know if you know. I see things that I didn't recognize as metal, gold, silver, right? So what are there more of? Metals or non-metals? Metals, more metals, right? Okay, so sodium chloride is an ionic compound because what's the metal in sodium chloride? What is the metal? Sodium. Sodium is that metal. Okay? Very good. So that allows us to recognize whether or not the compound is molecular or ionic. How about this one? Molecular or ionic? Talk to your neighbor. I'm going to go get a drink really quick. You need to get close to neighbors, so you guys need to find a way. Maybe a threesome right here, right? You need to, oh, you want to work over there? That's good. Everybody needs to work and find a way to talk to neighbors. Okay? Talking to neighbors, critical component. I'll be right back. Okay, so you probably, hopefully, have come to some conclusions about whether this is molecular or ionic. I'm going to throw in one more piece of information. Hydrogen, H, is an exception. It is not a metal. It's the only one on the left side that's not a metal. So what does that mean? Is this molecular or ionic? What's that? Where's the metal? What's that? No metals. Therefore, it is molecular. Very good. Yeah, question?
Actually, I think it just means it. So basically, every time it's a metal, so could you say, so everything on the left, you'd be like, that's molecular compound.
Everything on the left
Of the green.
of the green? Well, the left is this
The
green.
orange, the orange.
It's the green. The green is the staircase. And everything from that to the left is a metal.
Oh.
So if it contains those, anything from the green all the way over here to scandium, yttrium, zirconium, cubic zirconium. You guys heard of those, right? Big fake diamonds and stuff, right? So, yeah, anything in here, this is all metals, except for, what did we just say? Hydrogen. Hydrogen is not a metal. All right, so, good. We're hopefully learning, recognizing that there's different kinds of compounds, and learning the terminology is important. All right. Any questions about that?
I just want
Yes.
to clarify one more time.
Absolutely.
So all ionic compounds are metals and all metals are ionic.
Well, all compounds
Yes,
that contain metals
are ionic,
are ionic.
but not all ionic are metals.
Well, so a metal by itself isn't necessarily ionic, right? So, compounds, I mean, if it's just a metal, then it's an element, right? So what kinds of things are elements? Let's move this over a little bit to good. Gold. Anybody else notice? Silver. Good. Any other kinds of elements we know?
Water.
Water is a compound. Elements. Sulfur. Chlorine. Helium.
All the gas.
What?
All the gas sections.
Oh, which one? Which one are you talking about?
I mean, like, all the gas section are elements.
Well, we can do this. How many times do we do this? Play this game. 116 times, right? Because those are them. Those are all the elements, right? Now, that's a good question, though. Do we interact with anything that's elemental in our lives?
Yeah.
Like what? Gold. Okay? Gold's close to elemental. I don't know. 24 karat gold is elemental, but they don't make jewelry out of 24 karat gold very much because why? It's too easy to bend, right? So any of the jewelry that we interact with usually is less than 24 karat gold. And that yellow, really deep yellow gold isn't popular, really. It comes and goes, depends on who you are and stuff. Sometimes it's white gold. How do you get white gold? What's white gold? Yeah, what's white gold? It's like gold mixed with some copper, right? So it gives it a different color, and some other elements in there or something. So, there's red gold, right? This gold, fool's gold, this gold, I think this is either 10 or 14 karat. What is the other stuff in here? Mostly silver, mostly silver. Question?
So actually, all the elements are the pure molecule without other stuff. Like, yes.
A pure substance. Elements are pure substance. Or if something is elemental, that means everything there is that element. But I don't think that we interact with stuff that's elemental in our lives very much. Yeah, I guess that's true. We might breathe that every once in a while. Yeah, we fill it up with a balloon. That's a good example. That's a really good example. Probably as close as we can get. Even pure substances. Now, we'll talk about pure substances in a bit. So, those are our elements. These are not ionic. They are, some of them are metals, but they're not compounds. Compounds that contain a metal, then those are called ionic compounds. Okay, good. And we'll have lots of time to improve our understanding of this. Now, we want to have a little short conversation. Any more questions? We want to have short conversations about this slide here, which is the difference between mass and weight. Okay? Now, some people are really sticklers about calling it the right thing, or making sure you're saying the right thing when you're talking about either mass or weight. But it's not worth too much effort to care.
It's like a kilogram of feather versus a kilogram of steel.
Okay. Kilograms, right? So that was a joke we used to have as a kid. Well, what's heavier? A pound of gold or a pound of feathers? Right? And you guys remember that joke? The answer is they're the same. How funny. But then you hear other people say, what's heavier? A gallon of gold or a gallon of feathers? Right? Well, a gallon is a unit of volume, so the gold will be significantly heavier. So anyways, that's kind of the same situation here. When we talk about mass, that's something that is independent of gravity. But when you talk about weight, then it's dependent on gravity. Weight is actually a force that a mass will create. So, for example, if I have this person, and this person weighs 600 pounds, and I put him on a scale, and it says 600 pounds, I think that's 600 upside down, and he is on Earth, right? If I take him to the moon and put him on a scale same scale on the moon, what will it say? Not 600 pounds? The scale, the principle on which it works, is basically a spring, and as you push on it, it squeezes the spring, and the amount of squeezing relates to the mass, right? Supposedly. But it's really measuring your weight, because if you're on the moon, and it's not pushing it, it's going to tell you that you weigh 1/6 of that, which is 100 pounds. Okay? If I have a balance on Earth, and over here I have a 600-pound mass, and here I have my friend, right? Now I go to the moon, and I put my friend on a balance. How much mass am I going to have to put on the end of that balance? Yeah, it's the same 600 pounds. Here on the Earth, the force of gravity is going to be the same. Here on the moon, it's going to be the same on both sides. So, yes, I have less gravity pulling, so I'm going to need to have 600 pounds. I have less gravity here, but I also have less gravity here, right? I'm still going to need that 600 pounds. So this is the difference of a method for identifying mass and a method for identifying weight, right? And that's what the difference between those are. One is dependent on gravity and one is not. So if you go to the moon, do you lose weight? Yeah.
Oh, yeah.
That's why everybody looks so thin on the moon. Have you noticed that? Like the pictures, they look all really thin and stuff. That's all I can figure out. Or maybe they work out a lot. Maybe as astronauts they have to work out. Maybe that's why they look like that. I don't know. Anyway. Okay, so here's some pictures of some elements. Right, we got some gold. We got sulfur, carbon in the form of diamonds here. Right? All of this is carbon. All of this is gold. And gold, we need the gold atoms of gold. All of this is atoms of sulfur. Sometimes atoms, yeah, first. Chemical symbol. Quite a little mention about what the chemical symbols are. All these letters up here are just basically a couple of letters to represent the name of the the element. Some of them were recognized before English was the predominant science language. So they still have their Latin names, or they're named after their Latin names, like sodium, right? Na, potassium, K, iron, Fe. How about this one? Does this one remind you anything? Lead, Pb. What does that word look like? Anything, anybody? Plumber. Plumber, right? So that's where the term plumber comes from. There's other words that kind of relate to the elements like that. Okay? So we're not going to spend any brain power memorizing this sort of thing, right? We are going to spend brain power learning how to use the periodic table, which is always going to be in front of us. All right? And we've already learned a few things, right? We know that green line separates the what? Metals from non-metals. We know that titanium has how many, Ti, has how many protons in it? 22. How many electrons? 22. Okay? So that number tells us how many protons and how many electrons. Doesn't tell us information about the neutrons. We'll learn that later. Okay? Good. So we're learning a lot of stuff about the periodic table. We talked about a compound, right? Compounds always have multiple atoms in them, multiple kinds of atoms. A chemical reaction versus a physical reaction or a physical change. A chemical reaction, there's a new way, a change from left to right, and how the atoms are interacting with each other. Here we have a hydrogen interacting with a chlorine, and here we have them separated. Any change in how they're interacting with each other is a chemical reaction. Here, we're taking water with the little L. You guys know what that means? L refers to liquid, telling us that this is liquid water. And now we've made it what? Solid water, which we call ice. What's it called where you take water and make it a solid? Freezing, right? This is just a physical change because we haven't changed anything in terms of the interaction of the atoms within the compound here, right? Okay, so chemical and physical changes. Now, some elements are diatomic in nature. That means oxygen if I blew up a balloon full of oxygen, and I looked at the atoms inside, they wouldn't be atoms of oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Oh, let's stick with our little model here. Here's our nucleus. Here's our electrons. 1, 2, 3, 4, 5, 6, 7, 8. There's an oxygen atom. If I looked at them, I wouldn't see this. I would always see them 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Diatomic, we call it, going around in little pairs. All right? And that's because when they get close to each other, they can help each other out. They can stabilize each other a little bit, so they always travel around in pairs. And a lot of elements do this: hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. So that's something that you'll gradually understand. Yeah?
Would it come up when there's 3 oxygens?
3 oxygens is another allotrope of oxygens. This is ozone. You guys heard of the ozone layer? But that doesn't exist to a significant extent in our atmosphere, or sorry, our breathing atmosphere. We have an ozone layer at the top, a really small concentration, which does a huge, huge amount of good for us, right? But yeah. Okay, so looking at some of these chemical formulas, if I got this one here, tell your neighbor whether this is ionic or molecular. Tell your neighbor. And tell them how you know too. Right, go outside. You're not talking to your neighbor.
Metal that. Oh, yeah. Yeah. Oh, yeah.
Okay, molecular or ionic? Which ones are these? Okay, talk to your neighbor, tell them what you know. Okay, what's the first one? Molecular or ionic? Ionic, because what? It contains a metal. Which is the metal? The iron. How about this one? Molecular or ionic? Okay, did you talk to your neighbors? They all said what? Okay, talk to your neighbors, show them how you know what you know. Go. Okay, metal or ionic or molecular? Ionic, because what is a metal? Cadmium's the metal. Is that making sense?
Yes.
Everybody getting that? All right. What about this one? Molecular. Phosphorus is a non-metal. Nitrogen is a non-metal as well. Right? Okay, excellent. Now, can we identify how many of each elements are in compounds? Are we good at that yet?
Yes.
Okay. So, Na2CO3, why don't you with your neighbor identify how many sodiums, carbons, and oxygens there are. Write it on your little paper there. I'm going to go see if we can get, so who doesn't have slides? Raise your hand if you don't have slides. You guys got slides somehow? Okay, who? 1, 2.
Well, I don't have slides.
Yeah, so raise your hand. If you don't have slides, do not have slides. How many do I have to get?
Oh, yesterday, slides.
From the last class, yes.
Oh.
You do have those? I don't know if I picked them up last time, so maybe they're around here somewhere. So how many do I need to bring out? 1, 2 here? 3, 4, 5? Okay. 5 slides. Let's see what I can do. I'll be right back. Fill all these in with your neighbor.